When analyzing large datasets, the digit 1 appears as the first digit approximately 30.1% of the time. This observation defies the intuitive expectation that all digits from 1 to 9 should appear equally often, which would be 11.1% each. The digit 9, conversely, only appears as the leading digit about 4.6% of the time. This non-uniform distribution is known as Benford's law, or the first digit law. It applies specifically to naturally occurring numerical datasets that span multiple orders of magnitude. Think about the lengths of rivers, the populations of cities, or stock market values. The phenomenon is rooted in the multiplicative growth processes common in nature and finance, rather than simple additive processes. This statistical regularity provides a powerful tool for data validation. Benford's law states that the probability of a specific digit d being the first digit is proportional to the logarithm of the ratio of d plus 1 to d. Specifically, the distribution is logarithmic, not uniform. The probability decreases monotonically as the leading digit increases. The probability p of d is calculated using the base 10 logarithm. This logarithmic relationship ensures that numbers starting with 1 occupy a much larger interval on a logarithmic scale than numbers starting with 9. For instance, to transition from a number starting with 1 to one starting with 2 requires the 100% increase, while transitioning from 9 to 10 requires only an 11% increase. This inherent scaling bias drives the observed frequency imbalance.
The precise mathematical formulation for the probability p of the first digit d is p of d equals log base 10 of the quantity 1 plus the reciprocal of d. This formula holds true for d values ranging from 1 to 9. Calculating the probabilities yields 30.1% for the digit 1, 17.6% for 2, 12.5% for 3, and continues down to 4.6% for the digit 9. The sum of these 9 probabilities must equal exactly 100%. This law can be extended to analyze the distribution of second digits, third digits, and combinations of digits, although the distribution rapidly approaches uniformity after the first few positions. The second digit distribution, for example, is much flatter, with the digit 0 appearing most frequently at 11.97%. A critical property explaining Benford's law is scale invariance. If a dataset conforms to Benford's law, multiplying every number in that set by a constant factor, such as converting meters to feet or dollars to euros, will result in a new dataset that also conforms to the law. This invariance under scaling is a hallmark of logarithmic distributions. Furthermore, the law is approximately base independent. While the formula uses base 10 logarithms, the underlying principle applies regardless of the numerical base used to represent the data, provided the data spans sufficient orders of magnitude. This suggests the law is not an artifact of the decimal system, but a fundamental property of certain numerical distributions. Data that is uniformly distributed or constrained to a narrow range will fail this test of scale invariance.
Not all datasets obey Benford's law. For conformance, the data must satisfy several necessary conditions. First, the numbers must represent measurements or quantities resulting from mathematical combinations, not assigned labels or identifiers. Second, the dataset must be large, typically containing thousands of observations, to minimize statistical noise. Most importantly, the numbers must span several orders of magnitude, ideally 4 or more. If the data is artificially constrained, such as prices capped between 100 and 199, the distribution will be skewed toward the digit 1 and will not follow the Benford curve. Data generated randomly from a uniform distribution, like telephone numbers or specific identification codes, also fails to conform. Datasets derived from natural processes or complex human systems typically conform to Benford's law. Examples include the street addresses in large cities, the decay rates of radioactive isotopes, the molecular weights of chemical compounds, and the sizes of files stored on a computer network. Financial data, such as expense reports, stock market trading volumes, and tax filings, are classic examples used in forensic analysis. The reason these conform is that their generation involves multiplicative growth or exponential decay, ensuring that the numbers are spread logarithmically across the number line. When a quantity grows exponentially, it spends more time in the range starting with 1, for example 1,000 to 1,999, than in the range starting with 9, which is 9,000 to 9,999. Data that is intentionally generated, constrained, or purely random does not follow Benford's law. Examples include human height measurements, which are constrained to a narrow range, or the results of a standard dice roll, which is uniformly distributed between 1 and 6. Social security numbers, bank account numbers, and other assigned identifiers are designed to be uniformly random and thus fail the test. Furthermore, data that has been rounded or truncated significantly often loses its Benford properties. If a dataset is composed entirely of numbers starting with the digit 7, for example, due to a specific sampling bias, it will obviously violate the law. Understanding these exceptions is crucial for correctly applying the law as a diagnostic tool.
The primary practical application of Benford's law is in forensic accounting and auditing. Auditors use the expected Benford distribution as a baseline to detect anomalies in financial records, such as expense reports, invoices, or sales figures. If a set of manually entered figures shows a statistically significant deviation from the expected logarithmic curve, it suggests potential manipulation or fraud. For instance, if the frequency of the digit 4 is unusually high, it might indicate that an employee is fabricating invoices to stay just below a $400 approval threshold. This technique is highly effective because human beings attempting to invent random numbers tend to distribute the leading digits too uniformly, failing to replicate the natural logarithmic bias. Beyond finance, Benford's law is used to validate the integrity of scientific data and election results. In scientific research, if reported experimental data, such as physical constants or measurement errors, deviate significantly from the Benford distribution, it raises suspicion about data fabrication or selective reporting. Similarly, the law has been applied to analyze vote counts in elections. While vote counts themselves are complex and often localized, the total number of votes per precinct or the financial data related to campaign spending should ideally conform. A strong deviation, particularly in the distribution of the second or third digits, can serve as an initial indicator for further investigation into potential irregularities or systematic errors in reporting. The first documented observation of this phenomenon was made in 1881 by the Canadian-American astronomer Simon Newcomb. He noticed that the earlier pages of logarithm tables were far more worn than the later pages, indicating that people looked up numbers starting with 1 more frequently. Newcomb published a paper detailing the logarithmic probability distribution. However, the law is named after physicist Frank Benford, who independently rediscovered the principle in 1938. Benford collected and analyzed over 20,000 numbers from diverse sources, including the areas of rivers, baseball statistics, and physical constants, confirming the universality of the logarithmic pattern. His extensive empirical validation cemented the law's recognition and led to its widespread adoption in statistical analysis and fraud detection decades later.